Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, hello. Welcome to this hour-and-a-half session, putting real tools into the hands of students. Something according, yes, putting real tools into the hands of students. So we have 3 presentations, each a half hour. We might go shorter. We certainly want to go longer. I will be the timekeeper, but I'm also presenting the first piece of work, which is a model for concurrent and parallel programming. And this is done by folks back at Redmond, Sebastian Burkhardt and Dan Leijzen, who unfortunately could not be here, and with an intern, Alexandro Baldasin. After I give a little presentation, then Nikolai Tillman will talk about PEX for fun, and Nigel Horspool, there he is, will talk about try F sharp. Okay. So concurrency and parallelism is like the elephant with all its many parts, and everybody touching a little part and saying, well, it's, I think it's about this. We see that there's many ways of thinking about task and data parallelism. Microsoft, if you were at my talk yesterday, we have our own library called TPL.NET 4.0, a library-based approach. There are languages like X10 and Fortress. There's streaming languages. There's approaches for programming GPUs. There's MPI. There's all these different ways of thinking about structuring parallel computation on different platforms with different abstractions and different trade-offs. And in concurrency, then we also have many models. So we have sort of at the lowest level what all platforms share is some threads and locks, but then people build lots of abstractions on top of that, or in addition. So there's notions of these non-blocking things called futures or promises, and some experiments with these have gone to the extreme. We have transactional memory. We have lots of different ways of dealing with conflicts to shared resources. So into this is our focus, and I think what's really important is to focus a little bit on the domain. So when you're talking about GPU programming, there's the GP, which is the general purpose GPU, but the general purpose really is still fairly domain specific, because what you are doing is dealing with vectors and pushing vectors and vectors through operations, right? That's the way I think of it anyway. And so what our focus is not the GPU. Our focus is concurrent interactive applications which have large shared data structures and lots of readers and writers. Okay, so what would an example of that be? It would be something perhaps like Office. So you have an Office application, which is some very complex beast of objects and paragraphs and all sorts of formatting. Maybe there are many users who are simultaneously editing it. You have editors, so you want to react to events from the environment that are going to mutate the shared data. You want to do spell checking very quickly while the user is typing, so probably you'd like to do that in the background asynchronously. You might be every once in a while saving the file to disk. Just in case there's an error in the program, you can do a quick restoration, okay? And then you may be exchanging updates over the network with remote users. And there's a whole large class of applications that falls in this. So it's not about high degrees of parallelism, but lots of readers and writers to a shared data source. Another example, one we actually applied this concurrent revisions to, is a networked asteroids game in 3D called Space Wars. So this code came not from us, but from this book, And in this program, that's about 15,000 lines of C# code using DirectX. The original game is sequential, and we use this as a way to start playing with, what about transactional memory? If we wanted to make this thing concurrent using our latest STM.NET, which we tried, would we get some nice speed up in this game by using transactional memory? The answer was no, and it led us to the work that I'm describing today. So when we think of this game, well, what's going on there? Well, there's this game world, which represents the state of everything. So there's asteroids, there's the spaceship, okay? And then there's this physics simulation engine, which is going to compute over that. And there's a render task, which is going to generate a bitmap, okay? And those two things are sort of like the Office application. They're two actors on this shared data that have different goals. The render task wants to read the position of all these game objects and render things on the screen. The physics task wants to update the position of all the game objects. And it would be nice for the render task to actually see a consistent snapshot. You wouldn't like to have two asteroids that sort of appear to occupy the same position in space, for example. Another example in the game is a write-write conflict. So that's a read-write conflict. Another example is a write-write conflict. The physics task is going to update the position of all the game objects, but it's a network game where you can have multiple players flying their jet X-wings, whatever they are, through the asteroid field. So the network task is going to update the position of just a few objects in the game, mainly the X-wings, okay? But the physics task is going to update the position of all these game objects. So there's a write-write conflict, and one has to sort of determine how you're going to resolve those conflicts. Okay, so as I said, we experimented with this game in conventional concurrency control. When you have conflicting tasks, and you want to get some parallelism, some asynchrony, you have these sort of two approaches. One is to sort of start locking things, and whenever there's a conflict, just prevent it. But when you do that, then you're not going to get any sort of speed up or responsiveness, right? You're going to lock somebody out from firing a shot while the physics engine is updating, for example. That's probably not a good thing. So locking clearly wasn't what we wanted to do here. And then we thought, well, maybe TM is the solution for our problem. So if things don't conflict that much, like if the network updates and the physics updates really aren't interfering much, then there aren't many conflicts. And if the overhead is low enough, then maybe we can do this. So here with the optimistic concurrency control, we were hoping that we would not see, but even in the presence of the conflicts that we saw with the game, they just sort of killed the parallelism, the overhead of rollback and restarting. So both of these were for this game, for this setting of this shared data with mutators, readers and mutators, really wasn't going to give us some speed up, and we experimented with both. So the programming model that we developed, Sebastian and Don developed, basically has two main ideas in it. Revision is like a task. It's a logical unit of work that is forked and joined. And so, for example, the physics task might be a revision. And we call it a revision because we want that task to have its own isolated view of the state of the world, just like when you branch in a version control system, you get a revision of the world. So the idea is when you fork, you get your own logical view of the world as if it's all your own. And revisions go hand in hand with these isolation types. And the isolation types are these special types that provide this view. They're tied to the revisions. And it basically is going to lazily copy things from parent revisions in the version control as we need them, as we write to them. And then when we merge, as you'll see, we actually provide default merge operations through the types. So it's a library, and the correct usage of it is dependent on using these revisions and isolation types in particular ways, which I'll talk about. So the idea here in concurrent revisions is that you're not going to have conflicts between revisions that are operating concurrently. You'll never roll back because there aren't conflicts by definition. There are no restrictions on these tasks. They can be very long running, like a background task saving the state of your document or saving the state of the game so that you have a checkpoint. You have full concurrent reading and writing of the shared data, which is declared with the isolation type. And you get determinism at the join points by just ensuring that the join functions are true mathematical functions, and I'll talk about that. So it's a deterministic model, and there's all sorts of underlying things that Dan has done in the implementation to make it fast and space efficient using, of course, lock-free data structures and things to ensure that there's not much locking going on. Okay, so here's sort of the old world and the new world. So the old world is on the left, where we have a task, for example, in TPL, or think of it as a thread. And we have a shared variable x, and we create this task, and we start executing it here. And then the main thread goes on. We have an intermediate assertion, and then we join with the task that we forked off, and that join will block until that forked task is complete. So in the traditional view of shared memory, our assertion here, in order for it not to fail, we can view the value of x in one of two states. Either we see the initial state, which means that the forked task has not yet updated the variable, or it has. Okay, and then when we join, we know that after that, the value of x is 1. Okay, so that's sort of the traditional model. In the concurrent revisions model, this is what happens. Again, we use the special typing. So x now is a versioned integer. We have instead of a task, we have a revision, and the revision gets forked just like a task. But at this intermediate state, when we have concurrency, we see our copy of x. We don't see, because each revision has its own copy. So the main revision is like the main branch, and I've forked off this revision that can do something with x, but it sees its own copy of x. So in the intermediate state, I know x is 0 until I change it, until the main revision changes it. When we join, of course, x is 1. So side effects are only visible when the revision is joined, and there's deterministic execution. You might ask, well, what's the default behavior for this version variable? And it's that the child wins. So if the main thread updates, the child wins on the join, but you can change that. It turns out for the game and for many applications, the child wins is a good default behavior. But again, that merge function, which is a default, can be overridden by the programmer. Okay. But this guarantees deterministic execution. Simon? Oh, yes, so this is a library. So you can just like TPL, and all our other wonderful library approaches, you can generate lots of races and lots of bugs. So we would really like to have a nice type system and a language that would really make this all. But I will talk about a way we have for making it a little easier so that the programmer can't make mistakes. It depends. I mean, in the ideal case, so say you had a counter variable and you didn't really care about what the counter was, that you could tolerate the races. So again, it sort of depends. But in the ideal situation, everything is versioned. In reality, there's an overhead to the versioned version. Yes, there's a little there. Yes, this is pseudo pseudocode. But I will show you what the real code looks like in a demo. Okay, so on the left-hand side, no isolation. The value we see at this assertion is dependent on the scheduling, the thread scheduling, the underlying operating system. With isolation types, we declare the shared data, we fork off, we get a private copy of the shared state, which is this version state. Concurrent modifications are not seen by others. At the join, we wait as usual for the forked revision to terminate, and we write back the child changes into the main revision. Okay, so puzzle time. Here's a classic program without revisions, okay, and it has two variables now, okay. Let's think about what the semantics here are, and let's assume, I think in this example, that the increments are atomic, which of course in .NET is not true. Okay, it's easier to think about these this code in terms of the diagrams. So initially, x is 0, y is 0. We have two threads, or two tasks, and one is going to check if y is 0 and increment x, and the other is going to check if x is 0, and if it's 0, increment y. So what are the possible final values for x and y in our classic computational model? Okay, well, the idea is, well, we could execute things atomically in sequence. So we could see x equals 0 and y equals 1. Let me see if even doing this on the fly is difficult for me. Well, let's do the last case first. So it's possible to execute both in parallel, in both guards evaluate true, and then increment both variables. So it's possible to see x equal 1 and y equal 1 at the end, right? It's possible also that, and then the other two possibilities are where we order the two one after another. So if we execute this first, then x will be incremented to 1, and then this guard will evaluate false, in which case we get y equals 0 and x equal 1. But if this executes first to completion, then we get that. So three possibilities, right? Not very nice, really, when you think about talking to students and saying, what's the semantics of .NET code under sequential consistency? So then we can make things a little bit better if we had transactional memory. So if things were atomic, if we didn't allow sort of this interleaving to take place, but we had to execute the things atomically, we would get less behaviors, right? We would not have the possibility that x was equal to 1 and y was equal to 1 at the end. So you can see that atomicity helps us a little bit in the sense that it gives us less behaviors, but it's still dependent on the schedule, right? But if these things are versioned, then there's only one possibility, okay? And and that's that x equal 1 and y equal 1 at the end, okay? Because fundamentally, the main revision sees its own copy of y, and it increments x. The child sees its own copy of x and increments y. But the child doesn't update x, so on the merge, there's no conflict. The child overwrites, but the main revision wrote y. The child didn't write y. So it's perfectly deterministic.
Wasn't the child that said, if x equals 0, y plus plus x assigned 0?
Yes, we'll get to that. Okay, so it's all based on writes and not whether you wrote the same value or a different value. Now the thing about this is actually we're giving you determinism, but actually we actually at each point here we actually have a snapshot. So we actually have something at the intermediate states which is known in databases as snapshot isolation, but the conflict resolution. So by default for this versioned thingy, on a write-write conflict, the child wins, unless you override that. So in this revision diagram, now we're in the revision world. We had x initially 0, the main revision wrote 1, the child wrote 2, the child wins. The child writes 0, the main revision writes 1, the child wins. That's essentially your case, right? The child writes nothing, the main revision writes something. There's nothing to win for the child. There's no update.
Otherwise, you better be very careful not to eliminate their code.
Right. Okay. So that's how but that's always the case, right? Even with relaxed memory models. We can talk about that offline. There's a paper in PLDI coming up about that. Yes, one has to be very careful because sequential consistency is just an illusion that is not supported by hardware. So one has to be very, very careful. Okay, so there is custom conflict resolution. So this is very nice. For example, if you are keeping a counter and you want to do, say, parallel aggregation. So suppose you have this code, and now you don't want the child to win. You want to sort of join everything up. Well, what's really nice is in our branching, just like in a version control system, you know the state of the world at the time of the fork, and you know the two states at the join. You have a three-way merge in version control systems. You have the same thing in concurrent revisions. So at a join point, you can get access to the main, which is the value of the variable at the time of the fork. You can get, main is the value of the main copy at the join point. Orig, the third argument, is the original one, and join is the one from the child. And you can write a function of those as the final result. And it should be a mathematical function to guarantee determinism. It doesn't have to be associative commutative. It just has to be a function. So in this case, we would see the values 1, 2, and 0. You can see what our little that's supposed to be a lambda, by the way. I don't know what happened. So our lambda is basically saying main plus join minus the original value. Okay, Simon asked something about isn't it easy to mess up? And in fact, it is. When we write code, this is what it really looks like. Okay, you use attributes, and you say this I thingy is versioned, and this is what the code really looks like. But then it goes through a rewriter that basically looks at the data flow, and it puts the versioned around the int for you, and it finds all the instances of the i's, and it does getters and setters instead. So we can actually look at that very quickly online. So concurrent revisions is available via Rise for Fun. Let me see if we have the exact example. Well, I don't think we have the exact example. But here we have a version string, and otherwise it's basically just C# with this little attribute. The first step of writing this code is to run the rewriter. So the compiler first compiles it, then it runs a rewriter on the bytecode to sprinkle all the getters and setters and things, and then your code runs. But I see I'm running out of time very quickly, so I should finish up. I do not know the details of the rewriter. I don't think it gives you. I don't know that it has a soundness guarantee. So all the code that you call in .NET is a very dynamic concept. So I think you have to have all the code available sort of at rewrite time. And I don't know exactly, the rewriter is done statically. I don't think on demand. So it's probably, you could probably get in trouble pretty easily. Okay, so there's a bunch of demos that you can run on riseforfun.com. I just want to say that I already said a little bit about transactional memory and concurrent revisions. In concurrent revisions, compared to transactions, you focus on the data. You say, I want this data to be versioned, and the version data is what you get logical copies of at the fork, rather than sort of transactional memory, where you sort of say, I want this code to execute atomically. So we think that this is a nice approach that fits well with object orientation and a lot of patterns of programming. The implementation is a library. There's a whole bunch of stuff that Dan has done that I don't really can't speak to, but everything is done lazily. We don't copy the data on forks. We copy on the first write. There's garbage collection, of course, because you have all these versions hanging around. And we were able to take this game and with this main loop and parallelize it with all these, with this being the essentially revision diagram. So essentially we took collision detection on the asteroids, we parallelized that into 4 revisions. We have the main revision does the rendering. The very long running revision to save the state of the game gets branched off. This is per iteration of the game loop. So there's one frame going on here per iteration. The networking revision gets its own revision. Physics goes off, and physics updates come in. They win over render updates, but as you recall, render only does reading. And then you see collision detection comes in and can update after physics, and then the network sort of gets the last say. So in fact, the join order is how you sort of control priorities of updates. There are other ways to do that, but in the game, this was a very natural thing to do. Yes, the render task reads all the positions. Physics task updates the positions. There's no interference. And as I said, the network task updates the position of some objects, but it has priority over the physics updates since it comes in last. Order of joins establishes precedence. Wow. Okay, performance. The autosave, which is where? Don't even see it here. The autosave is in the background somewhere. The overall speed up here on a 4-core was 3 times. It's almost completely limited by the graphics card. You essentially see the collision detection, the networking, the physics update input from the network going in parallel. Okay, and I don't have time to go over the overheads, but we slow down the sequential case by 5%. Some individual tasks we slow down much more, but overall we get a nice speed up. So the conclusion, revisions in these isolation types simplify essentially how you parallelize these applications with tasks, task-based parallelism, where you have conflicting access to shared data, where you don't really know how long things are going to take, like the network, writing to disk, and your access patterns are not very predictable. The whole idea is you never roll back. Your conflicts are always merged in, but that's under your control. There's default behavior, and then there's the opportunity for the programmer to override that. And we find that the benefits of adopting this model are determinism. It's easy to reason about your tasks or revisions because they're fully isolated. And we've seen that in several applications that we've done, that we have low enough overhead to make even this library-based approach feasible. And I think that's it. If you have questions, please mail Dan or Sebastian. I'll take any now. You can play with revisions online through Rise for Fun, and there will be an external download of the library available very soon. Thank you. Christian. Oh, that's a good question. Nikolai, do you want to get set up while I answer? Yeah. So the first thing is they had to. The original game was sequential, so they had to parallelize it. right? So the first thing they did was parallelize it. If you were starting with an already task-based parallel program, you know, because parallelization by itself already is difficult. Once you have that, you do need to sort of identify what you want to version. And as I intimated, maybe not everything needs to be versioned. And if you version at a very fine level of granularity, the overhead might bite you. So if you have a huge array of integers, do you want to version every integer? Do you want to have the array itself versioned? Okay, so there's a notion of shallow versus deep versioning, right? And so then one is in all the pain of sort of data partitioning and those choices. So it's not simple, but the benefits, I think, you know, is that once you've done it, your debugging experience is much nicer. The performance can still be an issue depending on how many of these versioned types you have, how many of these versioned objects you have.
Okay. So Tom just showed you Rise for Fun, which is an online presence where we show all of the different tools that we develop in our group. And I will talk about Pyxis for Fun, which is basically the tool that started this whole online presence. And Pyxis for Fun has come the farthest way what we can do once we are on the web. Quick check. So how many have been to today in the keynote and have already heard a bit about Pyxis for Fun? Oh, pretty much everyone. Okay. Then I can skip some of the basic things. So I will talk a bit about why we did it, what's the point, and then how we, by coincidence, turned it into a game, and suddenly we had lots of users. And there's a bigger story to it. It's very useful for teaching. I will show how you can leverage it in your classes to teach computer science in a way that is actually fun and engaging. Not that your classes are usually not fun and engaging if you're teaching. So, so the background is that, so we developed this tool called Pyxis. It uses dynamic symbolic execution to generate test cases. I will explain in a moment how that works. And we go to conferences, we give tutorials, and then I want to do interactive exercises. So I would tell everyone, please now start your Windows laptops, launch Visual Studio, the professional edition, and then you install our plugin. And so basically, somewhere along the way, I lose pretty much everyone. So the whole motivation of the website is it's an easy way to try out our tools, in particular Pyxis, test case generator. So to illustrate that, you probably remember from the keynote, I can just type some code here. For example, I could have a function that takes an array and then index into the array, and maybe I say, maybe I just take an array that this should be equal to some value. Then throw exception. And then when I press a button, what happens is that we take the program, send it to our server in Redmond, and then on a class tile basically analyzes the program, and it tells me that I have a compilation error. And yeah, I shouldn't return a value here. That doesn't make sense anymore. So it's like a development environment, and when it succeeds, then it tells me all the things that can happen. So Pyxis has a definition of all .NET instructions. So in this case, C# gets compiled to MSRL bytecode .NET instructions. Pyxis has an encoding of all of these instruction semantics to an SMT solver, these three. And by doing a systematic path exploration and solving the path constraints, we eventually generate these 4 different test cases, which, according to the language specification, are all the different behaviors this code can exhibit. All the different branches get covered, and all exceptions get thrown. So you see that Pyxis knows about the exceptional behavior of the code. So now I could go in and fix the code. For example, obviously for null this crashes, so I can do something against that. And the length should probably be greater than 0. And then at least we avoid all of the implicit crashes. So Pyxis is a very useful tool to generate test cases in order to improve code quality. And Pyxis is available as a separate download. It also plugs into Visual Studio. And that's really how the website got started. So let me just kind of formally introduce how this works in the background. So given a program like the function we just had on the screen, what Pyxis does is dynamic symbolic execution. Another word for that is concolic execution. So Pyxis didn't really invent this scheme. That was already around for a while. What Pyxis does is it encodes the semantics of all .NET instructions. So it's the most kind of thorough engine based on this concept that I know. And it can reason about the heap in a fully symbolic fashion. So let's go through the steps of generating test cases for this function. So Pyxis is based on running the code and observing what happens. So initially you have to run the code with some inputs. And Pyxis always runs the code with the most simple inputs possible, null. The other approaches where you would start with random values, but I found that to be a rather bad idea. If you throw a random integer at the code, it might be used as a loop bound, and then it basically never terminates. So Pyxis always tries to minimize the inputs, starts with null. Then we run the code, monitor instruction by instructions what happens. In this case, we see that the program will return because a was equal to null. Then next time we want to do something different. So we select a branch. This is going to build up a tree. We are going to select a branch of what we haven't observed yet. And in this case, so we want to see that A is not null, right? That's the only thing we haven't seen yet. We basically obtained it by negating the constraint. Then we use our SMT solver Z3 from Microsoft Research, which has complete decision procedures for integer bit vectors and the heap and arrays. And then what do we get back? We get back a solution, if there is any, of this constraint system, which basically says we need a proper array, cannot be null. Now in principle it could be arbitrary in size, but again Pyxis tries to minimize the inputs, and the smallest array here is the empty array. We run the code again. We will run now one statement further. We discover new branches. We negate the last condition, and so on. Very systematic. And then after a while, we have a complete test suite, exactly what you saw earlier on the website. And in fact, here, there's no loop. So what we have is, in fact, a proof that this is all the program can do. There is no other behavior that we haven't covered yet. As soon as you have loops or recursion, the problem is undecidable. What test cases we would need to exercise all behaviors. In that case, Pyxis has bounds built in. So it uses a fair search heuristic to cover all execution paths equally until the bounds kick in. And one of the bounds is after 20 seconds, the website stops. So when you install Pyxis as a tool on your own desktop machine, you can run it longer, but the website stops after 20 seconds. Okay, so that's how Pyxis works. And one thing you might have already noticed is when I was typing, I get feedback in the browser, similar to how you get feedback from Eclipse or Visual Studio when you type code. So the intention of this website is that it can be used by students who might have a background of C, maybe C++, Java, but not C# yet. And what really is the biggest difference between these systems is the libraries. The syntax isn't so different, but the libraries. They're all named differently. Or let's say I want to do something with a string. Then when you want to take the substring of a string in .NET, it starts with an uppercase letter. So if I would type it in lowercase, it corrects me. So it doesn't look like much, but it helps tremendously in order to write code. So we have built in IntelliSense into the website. Okay, so we had this website out, and it was good to explain Pyxis. But then Taoxi had the idea of turning into a game. And you already saw in the keynote basically how that works. So the idea is that we take two programs, the one that we see in the browser, and another program that sits in the cloud. And then Pyxis is going to analyze both together, checking for semantic equivalence. And you have to change the program you see until you get it to behave the same as the one in the cloud. Then you win. So let's play that game together. So on the website, we have a learn section. This button is rather important. there's a lot behind that button. So in particular, we have here a list of coding duels. Let me go here. So we have a list of these exercises where we have, so each of these entries stands for one secret program in the cloud that we have to basically reverse engineer. The secret program is in the cloud serves as a specification that we have to implement. So we started, or we have more than 200 of these exercises on the website. They are ordered by how often they have been already solved. So the topmost one has been already solved 3,000 times. So it's the most easy one. All of the others have been solved less often, so they become harder and harder. So let's start with the most easy one. I'm sure that we can tackle that together. So here's a function that always returns 0. By the way, is it big enough for everyone to read, or should I? Yeah, okay. So this function always returns 0. And we can now see whether, in order to win the game, we have to implement the same behavior as the secret program in the cloud. But right now, we don't know anything about that secret program in the cloud. The only way to get feedback is by pressing the button for the first time. That sends the program to Redmond. We compare it for differences, and here is the result. So the result is that for the input 0, returning 0 is the right thing to do. So this is our parameter. And then we have two return values, ours and the one from the cloud. So for 0, everything is OK. But for 1, we return 0, but we should have returned -1. OK, that looks rather straightforward. So what would you say is a good way now to fix up this program to make it more like the one in the cloud, to have this input-output behavior? Any suggestions? How should I continue typing here? Return -x. OK, I already start typing. How should I complete this line to make it? So all this table really tells us is that if x is 1, we should return -1, right? That's all we really know. And so if I ask Plex again, what happens is that we do symbolic execution, discovering a new branch in the code. So we're going to generate one more test case, which is necessary to cover all cases. And that exposes another issue. For the value 2, the secret program does something else. So I could now keep going like that. And it's actually a very effective method. I mean, if the input-output behavior is not so obvious, this is the only way to get information out. You're really playing a game against an opponent which only tells you enough information for you to proceed one more step. So we will never win the game in this way. We have to abstract at some point. So if we had a fixed test suite in the background, then eventually we should win in this way, right? But we don't have a fixed test suite. The test suite is generated on demand. We basically have an infinite test suite, and PAX really looks for the behavior of the code. So somebody already said -x. And it's interesting that, so whenever I play this game with someone, they come up with slightly different versions. So there's -x. I could say x times -1. I had someone who looked at this hard for half an hour, and then he came up with this, which is also correct. So the point is that we are not looking for syntax. PAX is looking for the semantics of the program using an SMT solver, doing deep reasoning. So this is OK. I could have written it in any legal way. So now we win. And just to illustrate you that the constraint solver is working, let's say I make some kind of stupid bug where just for one value I do something wrong. So with a fixed test suite, you would never find that. But PAX looks at the code, so you get a custom counter example, and you don't win. OK. That is the easiest one. We could go on forever doing this. Let me show you.
If you win,
yes?
is there a guarantee that your program has the corresponding semantics?
Is there a guarantee that the program has the corresponding semantics? In certain cases, yes. So if there is no loop, if there's no recursion, and if all the data types we use, if we have complete decision procedures for them, then yes, there's a guarantee. But as soon as you have loops, recursion, or you use floating point values or strings, then we use heuristics. There's fair search strategies. If we cannot find a counterexample within 20 seconds, you win. So in practice, that works extremely well, because to trick our system within 20 seconds, you would have to write a lot of code, with complicated loops. And I mean, if you go through that kind of effort, maybe it's okay if you win.
Yeah, but,
Yes?
minus absolute x would also solve all the test cases that we have shown. It never tried minus 1 as an input.
So you say I should do a minus ups of x?
Yeah.
Okay. Let's see what happens now. So we didn't see certain values in the input yet, but the moment you basically force a behavior, we show you where you do it wrong. So not only did we find a value for which it's wrong, but also we show you the overflow exception that can happen, because PEX knows about all exceptional cases. So this was a game, a guessing game. And many people just play this game because it's fun. So we had already 450,000 submissions of programs. So people playing the game because it's fun. And we now have a user community of almost 2,000 people who signed in. So you can play the game without registering. But if you do register, then we can track your progress. So these are all the people who have signed in. So we have almost 2,000 users who signed in. And some of them have won an enormous amount of coding duels. So there are some people who spend hours and days solving these coding duels, and they won more than 100. So the number here means how many coding duels they have won. So sometimes, so we have a live feed that shows what's currently going on, who is doing what. And sometimes, so this is whoever is doing something in the world shows up here. Could be you if you are on the website right now. Sometimes we see that a user makes 8 years attempt to solve factorial or something more challenging, just because it's fun. So how can we leverage that now for education? So it doesn't have to be just a guessing game. It can be more didactic. So to show you one example, in our list of coding duels, we have, for example, a race sort. So here, it's not a guessing game what you're supposed to do. You have to write code that sorts the array in English, specification. But you still have to do it, right? So this description doesn't help too much. And obviously here, returning the identity doesn't cut it. So PEX discovers many issues where we didn't sort the array with the identity function. So whenever you're teaching algorithms, this can be very useful to let students do exercises by playing this game. And the student basically always has a teacher sitting in the back who is doing very pointed feedback. So it almost sometimes feels as if you were playing against a human being. Whenever you write code with some subtle bug, PEX will point it out. It's amazing. So let me show you how we took this idea of using PEX for teaching, how we took it to the next level. So instead of just having kind of random exercises, we created a way to have structured courses. So every teacher, so everyone here in the audience, can write these courses. So let me show one of them that was recently written, Jumpstart into Game Development with C# and XNA. So XNA is a library from Microsoft that makes it very easy to write games in .NET. And so before you let your students actually write interactive games, they probably should learn a bit about the concepts involved. For example, how to program on a 2D plane with points that have coordinates. So let me go into this course a bit. The course is structured in pages. Every page is a combination of descriptive text. So this is text that you as a teacher would write, introducing the concept of the 2D plane. And then it can be mixed with exercises. So here's an exercise where, given a target, x and y, and an edge of a rectangle, and the width and the height of a rectangle, we have to write code that determines whether the target is in the rectangle. So it's not rocket science, But you have to understand how that works before you actually write a game that interacts with coordinates. So when you have a class with content like this, what you get as a teacher is automated grading from PEX. Every class has a status page where you see the following. For every exercise and every student, so these are real people, you see how many times they attempted to win a particular exercise. Green means they eventually won it. Red means they didn't. You also see that maybe exercise number 4 has an issue, nobody won it. 5 seems to be pretty difficult. Somebody must have spent an enormous amount of time just because it's fun. If you're a teacher, you can also click on a link and see the last solution of the student. So you could check if maybe they all have the same solution because somebody leaked it. In the future, we want to do research to automatically detect clones. And if the student gets stuck, maybe some other student already got stuck in a similar way, maybe we can automatically help them to make progress. So this is just the beginning. We are expanding all the information that we can leverage to help the teacher in his course. Okay, that is a basic experience of teaching a class. Maybe let me show you one more thing. Let me sign in so that I can actually, let me sign in as a teacher so that I can actually edit something. So you need a Windows Live ID, it's basically a Hotmail account, to sign in. And I'm sure if you're all having Windows phones now, you have a Hotmail account, or at least you should. That makes it much easier. And now I'm signed in. You see that my menu suddenly has many more options. So PEX keeps track of all the exercises I've done so far, the coding duels. As a teacher, I can edit pages that have content and exercises in it. Pages are combined into courses. And as a teacher, I can get an overview of all my students, what they have been up to, what they did. So let's edit a page together, which you might want to create as part of a course. So here are all the pages that I own. And I could go to, where do I go to? What is a good one? Let's try loops. So it's a page. It introduces the concept of loops. It has an exercise in it. How would you edit it? So I have to click some buttons here to make it editable, and then edit. It's basically a wiki syntax. It's very easy to use. And you can mix code using some meta information where the code starts. You can mix that with text where you describe concepts. And it's very easy to plug in an exercise. You give the starting point for the student that he sees. So this is a template the student would see when starting an exercise. And down here in the hidden portion is the secret program, the specification that the student would have to reverse engineer. So it's very easy to plug in new content. Okay, let me lock this page again. I think I have shown pretty much everything about the website I wanted to show. Do you have any questions about the basic experience and the capabilities? Maybe about the capabilities, one fun example that shows you kind of what you can do here. So everything I showed you so far was basically one function. It doesn't have to be just one function. You can have more. So let me go to some other puzzle. So for example, here's one credit card number. So here I have multiple functions that call each other. So the main entry point of the puzzle is here, takes a string. First it checks whether the string comes from a particular issuer, which means it starts with a certain number. And then for each issuer, there's another constraint, a checksum constraint. which is implemented in yet another function coming down here, which computes a linear combination of all the values. And if that's correct, it's potentially a valid credit card number. So the question is, can PEX come up with inputs that pass all of the validation checks, including the checksum algorithm, in order to cover that statement? So PEX will systematically explore all of the branches in all of the functions. It's a transitive interprocedural analysis. Let's try it out. I wouldn't show this example if it wouldn't work. It's trying to cover all branches in the code. I mean, eventually it will enumerate all paths. But the intention, the test cases you see, are at most one per branch. So the test suite is limited in size by the number of branches in the code. It's linear in the size of the code. But internally, to achieve that, PEX would eventually have to enumerate all paths. I mean, it might be that in order to cover a branch, you have to go around the loop many times. So PEX will keep going around the loop until finally it manages to hit another branch. So internally, PEX enumerates all paths, but the test suite only tries to achieve branch coverage. We can talk more about that offline. So what you see here first is that PEX systematically covers all the issuers, and then after a while, it makes its way through the checksum algorithm, and this is a valid credit card number. And you only get it for one issuer, because in order to achieve full code coverage or branch coverage, where we only need to look at the checksum algorithm for one issuer, because it's always the same algorithm. So we don't get a huge test suite, but it's actually rather neat, and just a minimum number of tests to, well, minimum in some sense, to cover all the branches. Okay, another little detail. So the PEX engine works at the level of .NET MSIL bytecode. So we support not only C#, but also Visual Basic and F#. You will hear more about F# in a moment. I'm showing you everything in C#, but it works just as well in the other languages. So let me show you one thing, finally. So you all got Windows phones, right? And I'm sure you already installed Touch Studio, because you heard about this great Windows Phone app in the morning. But we have more. So let's see if I can get this on. So another application you should install from the marketplace is PEX for Fun. It's this little fish here in the upper left corner. And it's basically implementing the same experience as a website, but on the phone. And it's very customized so that you can more easily play the game with your finger. But then again, if you try it out, you will appreciate how easy it is with Touch Studio to write code. Because here it's still basically editing C#, VB, or F#. So I can say play, and it tells me how the game works. And then I get a list of all the coding duels that we have on the website. And I could pick one. So we already have solved this one before. So we should be able to do it again. So right now it's actually not a legal program, it tells me. What is wrong? Semicolon expected. Does anyone see why I need a semicolon?
We can't see. Yeah.
It's totally overexposed. Bummer. So let's run PEX on it. I think it might have been an outdated error message. So I win. So whatever was overexposed just a moment ago, it was basically -X, so we won it again. And then you can keep playing the game. And it's amazing, even though, so I cannot really show you the experience because it's overexposed, but even though it's still pretty tricky to enter C# code, it's always very small, and thousands of people have won coding duels on the phone, so you can try it too. Okay, and with that, if you have questions. Yeah.
So I have a comment that this could also be viewed as a test-driven development kind of feedback practice.
Yes, so we got that feedback from other people too, that this is test-driven development in action. But it's an interesting version of test-driven development because somebody else already basically wrote the tests for you. All you have to do now is implement the program correctly, which I think misses the part that, I mean, test-driven development is about writing the tests to make sure that you have a good design. You're missing that step. But otherwise, yes, it's connected to test-driven development. But in some sense, the implementation here in Packs for Fun, it serves as a specification. It doesn't really matter if it was given as a program or if it would have been given as a contracts, pre and post conditions, or maybe in a totally different paradigm. For all the user knows, there is a specification in the background, and he better fulfills it. Oh, okay. Say the question again?
There might be many different control programs
Yes.
that you could perform. This is one of them, right?
So PACS will systematically explore all control flow paths in that sense.
But that's only statement coverage of branch coverage. There are other possibilities also.
Yes, so internally, PACS will explore all execution paths. So it does every coverage notion you can think of. But
Branch coverage, right?
yeah, and if you download PACS, you can configure in more detail what kind of tests you want. On the website, it's looking for branch coverage because that's all that's really needed to find mismatches. There are ways for a teacher to configure PACS. As a teacher, you can also write assumptions. So let's say you don't want to bother your student with null reference exceptions. You can write in the reference implementation, assume not null. You can also say set this bound to that value. There are some options like that, but they haven't been requested too often yet. It's kind of a hidden feature. You will use it, yeah. Okay, then I hand over.
Maybe I can be heard. Okay, I'm Nigel Horsfall, and I was only one member of a fairly large team of, about 10 people who worked on this Try F# project, so I feel like I did the smallest part of the whole job here, and yet I get to speak about it, so I will try and give due credit to everyone when the time comes. So yesterday, Don Syme gave a 3-hour tutorial with his PhD student Thomas Petracek on the F# language, and today Dean and Christoph were giving the demos of the Try F# website, so you folks have probably heard an awful lot about it already. I'm not going to be talking too much about F# itself. I'm going to be talking about sort of the Try F# project itself and how it might be used in education. Do this. So just to remind you, in case you missed the tutorial, so F# is a language designed by Don Syme, has done an amazing job on putting together a language that is mostly functional, but pulls in other paradigms where needed, where useful, to produce a much more productive language. If you're looking for the antecedents of this language, he was probably mostly influenced by OCaml, Objective-Caml, as indeed was Scala. But Don, his focus was really to produce a language where you could be very productive, so he was looking for concise language with the full power of the .NET framework, so it can access all the libraries and get a lot of work done, and produce a tool that's really good for developers, and of course, should be very good for teaching as well. In fact, he did such a great job on convincing Microsoft about the future of this language that it's become a full member of the .NET family and has been fully integrated into the Visual Studio 2010. And, of course, now that it's there, Microsoft wants people to actually use this language, and so Try F# is part of that strategy to try and promote the language a bit and get it out there and make it easily accessible to everybody. Now, if you want to install F# on your computer, you can do it regardless of platform. Don Syme has been quite vehement about the language itself being platform neutral. It must not be a simple Windows product, or else it's not going to get wide acceptance. He wants it to work on everything. And so you can install it on Windows, of course, and if you have .NET, or if you don't, you can install .NET, and then you can add a package which adds F# to your .NET environment. Or if you install Visual Studio 2010, you'll get F# automatically. And if you're using Mac OS X, or if you're using Linux, it's pretty easy to get F# working on those platforms as well, because you can install Mono plus the F# download to get it all working. Or if you like to use an interactive development environment, something in the spirit of Visual Studio, you can use Mono Develop and add a simple F# plugin to it, and it all works. And indeed, the F# compiler, the F# interactive system, is all open source software. This is all part of Don Syme's strategy for making the F# language totally available to everyone. No surprises. As open source as he can make it. Now we get onto the subject of promoting programming languages. So if you look around a bit, you will find that some programming languages have got some nice introductory websites available to them. You can find that there is a website called trypython.org, and you go to that website and you can find that it gives you a tutorial introduction to the Python language. You can type in little code snippets in Python and see them actually run. Very nice website. Similarly, you can find the same for the Ruby language. You can find it for the Haskell language, very nice functional language. And you can find it for Scheme, another functional language. These are all websites aimed at beginners. They give you tutorial introductions, and they let you run code samples. One thing they've all got in common, actually, is these are all interactive languages. They can all run in an interactive mode where you can type a few lines of code and see the result immediately. Now, F# is available in exactly that mode. There is F# Interactive, which you can use in an interactive environment, type a few lines of F# and see the results immediately. So therefore, it seems reasonable that we should have a Try F# website that joins this family. And of course, once you start thinking about having this a Try F# website, you start wondering about how it might be implemented. So one basic decision you've got to make is, that if you're typing in some F# code, where does it get executed? Is it done on a server, like the Pex for Fun site that we've been talking about just now? Or is it done totally on the client side in your browser? And interestingly, of those 4 websites that I just pointed you at for 4 other programming languages, they actually chose different choices. A couple of them are done on the server, and a couple of them are done on the client. So obviously, there's some trade-offs involved, and we will come back to what those issues are in a moment. When we're building the Try F# website, we have some goals in mind, and so looking at it with sort of in retrospect, it's easier to state what the goals are than before when we started. So the goal is to give a good feel of the language to anyone who comes there. This is a starting point for learning about the language. You want to sort of give a feel. You want to get an introduction to the language with a tutorial that's sort of easy for anyone to read. And you want the ability to actually try out some F# code and see what happens. And of course, if you get excited by this tryout, you will obviously want to go and learn more about the language. You probably want to go and install it on your own computer, that kind of stuff. So we have a lot of links to further resources and help and information to tell you everything you need to know. Now, in part of this philosophy that F# should run everywhere and be sort of platform neutral, we want the same thing to be true for the Try F# website. That is, it doesn't matter which operating system you're running on your computer when you go to Try F#. It doesn't have to be Windows, and it shouldn't matter which browser you use. So as far as possible, it should be neutral for the platform and browser. And the design decision here is if I have a class of 100 students and I point them all at try F# and tell them all to use it. I don't want them to sort of slow a server down to make it really slow when they're all trying to use F# at the same time. So that sort of pushes you away from doing a server-side solution. And especially because F# is a programming language, and I can easily write myself a sort of recursive loop or something that uses up a lot of CPU time. So it seems much more scalable if you give the work to the client. So we want to actually execute the F# in the browser as much as possible. And keyed in with that is obviously some security issues. That is, if you're letting the F# code run on the server, you've got to be very careful about what kind of code is being run. And if you're running it in your browser, you can be a bit less careful. There's more things you should be allowed to do. And of course, if all the work's being done in the browser, then you don't need so much support in providing lots of servers for this particular service. So this means then that try F# is actually done as far as possible in the browser on the client, and in other words, on the client end. Now, as it happens, Microsoft has got a wonderful product that makes this really quite feasible. And this is the Silverlight product. Now, I am not a Silverlight expert. I had to go to Wikipedia to learn a lot about this, and the more I read about it, the more it was quite interesting. But the one-line definition is that this is a rich application framework for internet applications. It's intended to be used with browsers and to give access to multimedia. You can display videos, produce sound, but more importantly, we can actually display graphics here and display text and do simple things that we actually want for our try F# website. So we have got Silverlight available. We can use it as a browser plugin. Coming with Silverlight is, in fact, a large subset of .NET. That is, it will execute .NET code and comes with a subset of the .NET libraries. So in other words, it's pretty usable already for running F# code, which is a .NET language. All you've got to add to this is the F# interactive, the FSI code, and a little bit of glue to make it all stick together, and you have got everything you need to run on the client end. A little bit more about this is that it's easily scriptable. That is an extended application, application markup language, XAML. You can specify how the web interface looks, in other words, how it's all displayed on your screen. And you can script it in different ways. So this made it really easy to set things up for try F#, and it will also make it easily customizable if other people want to take the code and modify it for their own needs. Silverlight itself is produced by Microsoft to run in Windows and Mac OS, so that's easy. And then there is a version for Linux called Moonlight, which is almost up there, but has actually caused a few problems. Get to the next one. So what happens when we visit this try F# website? Well, if I'm grossly oversimplifying here, but when you first go there and you click a begin button, it will check to see what operating system and what browser you're running on. That will, of course, then determine what's needed to be installed on your computer. So you need to have Silverlight installed, and so it will check and perhaps force you to download what's needed to get things going. And then once you've set up your machine with some very simple downloads, then it will install the plugin that you need to then run the try F# website. And of course, I've grossly oversimplified. Now I'm going to actually go and run try F# for you. So I've just got your list of points that I'm going to try and demonstrate to you. Of course, this is where things might go wrong. So I have to escape from here. I have to go down and find my browser. So up comes a Firefox browser here. You won't do it all in Internet Explorer. And this is the start page of try F#. Gives you a few words about the language, a lot of pointers to various resources for doing things. But more importantly, it's got this begin button over there, which is supposed to attract your attention and encourage you to click it. And it brings up immediately an explanation, a welcome message on the left. And it sort of went fairly quickly, but there was sort of progress bar that indicated the checking stage and download of the plugin for my browser here to make it all work. And when it had finished, it brings up a code window at the top of the right-hand side where F# code is supposed to be entered. And the bottom half of the right-hand side shows the result, the output from the F# interpreter, the FSI command. Now, I'm not teaching you F# today. This is not my job. That was Don Syme's job. What I'm trying to going to do is to show you how easy it is to just sort of browse through this tutorial. So there is a topic index for this tutorial. You can pick, you can go through those different topics in order. But let's sort of jump down a bit and see if I can find myself a little example program. And we will show you how easy it is to run. So here's a very simple demonstration of how to create some lists. So if I want to actually run that code, I can click load and run. And what happens is it got copied to there. And because it said and run, it also did the run button for you automatically and produced the output from F# down the bottom. Now, what could be easier for getting some sample code running? Okay, and let me go on and pick something else to try out. Do we have something more complicated down the bottom here? Okay, here's code that's not quite ready to run yet, is it? Let me go back up and find something different. I want to do a more complicated one down here. There. There is a bigger program that I've got in the tutorial. Copies, and it runs. Now, you're not restricted just running the code that appears in the samples. If I want to try something else, like I wanted to, what shall I do here? Well, I've got a function called square defined. Let us type in here square of 4.4. I can highlight it, and I click run, and it executed and produced the answer down the bottom here. So it's very easy to type in little bits of code here, just highlight the bits you want to execute, and it sort of gets added to the computation, evaluated, and the output produced. So this is meant to encourage the users, the students who are going to be using this system, to play with the code and just see what happens. Now I'm going to sort of show you a few more things here. Up the top right-hand side here, we've got sort of 3 different ways of displaying the screen. So we can go into sort of a 3-column mode here, where there is an index to tutorial permanently down the left-hand side, the tutorial material in the middle, and still we got the code windows on the right-hand side. If you don't have a wide enough screen to accommodate all that, you can go to back to the two halves and still have access to tutorial by going to the topic index. So it's all there. And if you're not interested in the tutorial anymore, you've read everything you want to read, you can turn the whole screen into just entering the code, producing the results down there. Okay, now I thought I would show you a couple more things. So one of the features we've got here is the ability to open files and load in some sample programs. So here I've got a really short one that's, okay, let's open that one. And what I've got here is actually a very nasty bit of functional programming using lazy evaluation. This took me a while to debug and get working, so even though it's only a few lines of code. But what I wanted to demonstrate for you is that it can run. Oops, I don't know what happened there. And it produced for me the first 10 Fibonacci numbers in the window down there. 1, 1, 2, 3, 5, 8, blah, 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 blah. All right. That's all intended. And now I'm going to do something that that perhaps we shouldn't be doing. Let's see if I can type it in up there. I am going to give myself an infinite loop, and let's see what happens. I want to do the whole Fibonacci sequence. And this will actually run fairly slowly because I've got such a horrible recursion. It will go slower and slower as the numbers get bigger. So there, I've typed it in. I am going to run this code. I want to highlight it. Oh, come on. I'm not very good at doing this. Ooh, and it's going slower and slower. Now, how do I stop it? Now, just imagine this running on your server and making its performance grind to a halt. Well, I can just right-click here and say cancel evaluation, and it kills the program. So that's one feature there. We can exit from infinite loops. If this was the answer to one of my problems being posed to me by the instructor of a course, I can go over here and I can save the contents of the code window as a new file. So this could be my answer .f# and save a new file. Okay, and that's a way of submitting work back to the instructor of my course. Well, what else can we do here? There's this little button over the right-hand side here that's labeled Canvas. That's to produce an optional canvas for graphical output. And let us make it a bit bigger. And what can we do in there? Well, we've got some sample code that's already provided on the system in the tutorial. So if we go back to, let's not do that one. Let's load it in directly as another program. So here, this is one that was nicely ported by Christoph, I believe, to work in try-F#. So this is a really long piece of code, and it plays a game. This is bound to get the students amused. So starting to run. OK, now over on the right-hand side here, we have got a game where it's quite amazing. Let's click to start. And now all these missiles start coming in from outer space, and I've got to try and stop them with my defensive missiles. And here they come. Bang, 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 bang. Right. OK, and eventually all those missiles coming in will overwhelm my cities, and I've lost the game. But that illustrates, the power of the system here for displaying graphics and giving interesting assignments to students. So you can do a large subset of the F# language here. I've lost a city on the right-hand side already. Well, I think we can quit that now. So, OK, so let's kill it. I didn't do it. How about that one? Still not doing it. Help! Clear canvas. There we go. So did I show you everything there? I think I did. So back to my slideshow. And comment slide. So what I hope I've convinced you is that what this try-F# website provides is an easy way for the students in your class to run F# exercises, to learn the language, to become enthused about functional languages in general, perhaps, and is completely neutral for the platform you're using. That is, in my classes, for example, the students have got, some of them have got Windows machines, some of them have got Linux machines, some have got Macs, some of them have got virtual machines allowing them to run multiple operating systems. It's just totally unpredictable what my students have got. So it's really important that we provide a service like this, which is platform independent. Otherwise, I couldn't use this tool in my class. Now, there's a little sort of footnote here is that the Linux version of this website isn't quite working because there's some incompatibility between Moonlight and Silverlight. So the Moonlight has got to be upgraded a bit and some deficiencies solved before it will all work correctly, but it's coming soon. So I would recommend this website as being great for first-year courses or even for later courses at university where you want to learn something about other programming paradigms. If you started off with object-oriented or imperative and now you want your students to learn functional, this would be really good. It provides a tutorial introduction to language, and you can have the students run your exercises and send you the output. Now, if you don't like the way we set it up, it wouldn't be that hard to modify it for your own purposes. That is, it wouldn't be too hard to host this website on your own server if you wanted to. It really wouldn't be too hard to modify the tutorial material. You could extend what I provided there or edit it. And if you don't like the layout, you can modify the XAML code to change that as well. So it should all be customizable without too much effort. In fact, the tutorial there, divided up into about 5 sections, was originally coded in a fairly simple notation called Markdown, which is just standard text using sort of asterisks around words to put them in boldface and some very simple little extra markup to give it some meaning. And it can be automatically translated to HTML, which is what, of course, the Try F# website is actually displaying for the tutorial. So I think I'm coming towards the end here. The status of the project at this moment shows the compatibility of the Try F# plugin with the different browsers and the different operating systems. You can see there's a lot of yeses in there and a no. I guess that's not going to be supported, and a few not applicables. So it's a pretty good compatibility. And coming to the end here, Try F# for me seemed to be ended almost as soon as it began, before we got everything implemented. You know, it would be really lovely to carry on and do some more work and make the Try F# website even more powerful. And I've got here a list of points where maybe it could be improved a bit or extended a bit. So, for example, the tutorial where I was the mostly responsible person just is not enough. You know, I would love to extend the tutorial to cover the whole F# language instead of the fraction that we're currently covering. We're limited a little bit in what class libraries can be used by the F# code in the Try F# website, because Silverlight only gives you a subset of all the libraries, and there's also a couple more restrictions for security reasons. So we can't use absolutely everything that the normal F# program would be able to do. So it would be great to extend Try F# to give us a bigger subset. Don Syme would really love to see IntelliSense added to that code window where I can add some code. So if I can type in code and have suggested completions there, just like with Visual Studio, to say how to carry on and what members are in the library and things like that, that would be absolutely wonderful. And if you tell me my syntax errors as I'm typing it in as well, even better. Thinking as an instructor, it would be really nice if one of the ways I could customize this website easily is to add my own exercises and quizzes for grading for my class, for the students. So if I could just have that as an option as instructor, so I could say, you know, my students will see an extra button, say quiz 1, quiz 2, quiz 3, and so on, and have the marks automatically emailed to me when the students click the submit button. That would be fantastic. And it really would be nice if Try F# was allowed to grow as users out there in the world added the material themselves. So more code examples would be wonderful if we had sort of a section here with user-supplied code. And there's even more ideas for how to extend this Try F# website itself. But these are the ones I'm focusing on for educational purposes. So in case you forgot that URL again, there it is. I want you all to go out and try it. You know, it is, you can have a lot of fun if you've never played with F# before. And I would like you to send feedback when you find that there's omissions and errors and things, so that we can improve the website. So at that point, I'm done, and thank you very much. Any questions? Yes, sir. No, it's added on separately. So actually, I've got the two experts sitting in this room. So Christoph, the F# compiler is actually the download that comes when the green bar is running across, isn't it? Yeah, yeah. So Silverlight should be in your system as a separate install, like it's added to Windows as a sort of a separate add-on, and then the plugin for the browser comes in with the F# compiler. Yeah. Anything else?
So there were a couple of points you made for extension.
Yeah.
So code for fun could be combined with this to come up with that one, right? You said instructors should be automatically evaluating the.
It would be great if this actually sort of ran your F# code and saved the code with the output and could email it to the instructors so that you could use it for grading purposes. I would just love to see that in my class. Yeah.
Automatic grading could already be
well. Automatic grading sort of rather restrict you on the kind of programs you could set. You know, like you could check the output to see if it's correct output. That's for me, that's only a partial mark. You know, I'd actually want to see the code as well. Yeah. Anything else? Okay, well, I think the session is about over then. Okay, thank you.